Okay, completing that short run through the nitrogen cycle, carbon cycle, nitrogen cycle interaction, nitrous oxide feedbacks, we will move on to methane, which is another strong global warming greenhouse gas. Obviously, you have already heard of the various sources and sinks. You have anaerobic oxidation by microbes, dry soil oxidation, where methanotrophs can combine CO2H2O to produce methane, and you have methanogens in soils as well. And wherever you have decay of plant and organic matter, or places like rice paddies, you have methane production. And in the atmosphere, you have often decomposition and formation of methane, or interactions with isoprenes, as we will see later, where the hydroxyl radical is taken away. Then the conversion of methane is delayed, so life cycle of methane can get extended. Fossil fuel burning produces methane, especially coal burning. There are melting permafrost, thawing permafrost, which can release methane. There are digestive processes in domestic animals. The ruminators produce plenty of methane. They're a significant source of methane. There is transfer of methane in soil to air by plants, and so on. So this is the general methane cycling. Hydrates and clathrates we will look at a little bit later. We raised that as a potential source of CO2 in the Paleocene-Eocene thermal maximum. Methane, we will see, is being emitted over all these places. For 2016 estimate from Our World in Data. That's a great source. So they're measured in tons of carbon dioxide equivalent based on a 100-year global warming potential value we talked about before. So these are the ranges we are looking at. So there are tropical countries which are strong sources, but also peatlands or permafrost regions can be strong sources, and of course large production of beef and other ruminating animal meat can be a big production of methane, and so on and so forth. Okay, emissions from peatlands by country. Peatlands are like a form of wetland where peat, which is a partially decomposed organic matter that gets buried, then more falls on top, it can get compressed and become coal over time, and so on, has a million tons CO2 equivalent in these ranges across. Peatlands are everywhere, so you can see that many countries have peatlands, especially here in the permafrost regions, and they are obviously a potential source of CO2 and feedback to the atmosphere. So if we look at the global greenhouse gas emissions per type of gas and source, including land use and land use climate forcing, land use change forcing, we can see in gigaton CO2 equivalent. I hope you understand. Methane is not CO2, but you can convert it to CO2 equivalent using the amount of CO2 would be produced if you burned it, and so on and so forth. There are scientific ways to convert the greenhouse effect into CO2 equivalent. Okay, so land use and land use change and forestry. Sorry, I said it wrong. So forest and peat fires. Peat fires can smolder underground for long time and produce lots of N2O and methane, as we will see. Land use change, so conversion of wetlands or rice paddies, and of course grazing cattle, and so on. So you can look at total emissions excluding this land use change, and forestry. You have various sources here from energy, industrial processes, agriculture, and so on. And over the 1995 to 2016 or 2017 period, there has been an increase in CO2 from the energy. and of course also N2O from agriculture and industrial processes, and methane from waste and other agriculture and energy. Okay, so this is something to keep in mind when it comes to global methane budget. These are the total emissions, 540 to 568, so there is a bit of uncertainty there. So these are emissions by sources: agriculture waste, wetlands, fossil fuel production and use, so leakage happening at oil well site and so on. Natural emissions from geological leaks, lakes, termites, which convert organic matter into methane through respiration and fermentation, oceans, permafrost thawing, and biomass burning. The sinks, there are a total sink of 548, so you have some that is being released into the atmosphere, 10 units here in should be million tons CO2 equivalent, if I'm not mistaken. Please look it up. So sink from chemical reactions in the atmosphere. So methane is highly oxidizable, so easily gets burned off into carbon monoxide and then carbon dioxide. And of course there are sinks in soils as well. Okay, so that's the methane. Wetlands are major contributors to methane emission, like peatlands, which are a form of wetlands, and you can see these sites here: salt marshes, mangrove swamps, major wetland areas, and areas of concentrated wetlands all around the world. Obviously mangroves are a lower latitude thing, and salt marshes are higher latitude features typically, and the distribution of wetlands very much depends on climate, temperature, precipitation, and so on. So people have made models of how many more acres can be potential sites for wetlands. Obviously humans have drained large amounts of wetlands. Wetland loss is very high. For example, state like Florida is mostly built on drained wetlands. Even DC, I think, was a wetland, a swamp, before it was drained to build the city. The models do try to capture these. So these are this is a summary of methane models and their main features. These are the various models by name. Hadley is in the UK, for example. GISS is the NASA Center in New York. IAP is in China, and so on. So they have dynamic wetland. So they have wetland processes represented explicitly. Rice paddies are included in some explicitly. Permafrost, methane increase specified, and carbon accumulation and loss, whether it's represented or not. So these are specified perturbations, and these are the climate scenarios that were used in the AR4, or the fourth assessment that came out in 2007. The latest one came out in 2014, but this book was written just before those came out. But these models have, many have improved, many more models have included more dynamic processes. So this is looking at methane emissions as simulated by one of the models, the ORCID model here, and you can see it has no rice paddies. It has the one version has permafrost, the other one doesn't, and so on. This figure was first published in 2011. These are the control emissions. These are additional emissions by 2100 because of atmospheric CO2 increase. So this is now carbon cycle impact on methane emissions into the future in 2100. So CO2 will be used to increase temperature, change precipitation. There will be land use assumptions going into the projections and so on. But this is the net effect going from there to there. Okay, and C is the additional emissions by 2100 due to just climate change. So in the models you can do a CO2 forcing to do climate change and not allow the carbon cycle to respond. So turn off the carbon cycle feedbacks, or you can have the full carbon cycle feedback and look at both the influence of CO2 increase and climate change. So these are the sensitivity experiments, as they are called, give you a sense of how fossil fuel CO2 increase as done in these scenarios into 2100 will affect climate, how that will affect methane, and how the carbon feedback will influence the climate change, and how that will influence methane emissions. Of course, you can then do impact of methane emissions on climate as well, and in fact it should be done for getting a handle on the total feedback. So this is the additional emissions by 2100 due to the combined effect of CO2 and climate. Okay, so that's how you separate different components of the feedbacks. As we said before, actually validating these is tricky, especially when you make future projections. You have to give some sense of uncertainty involved. This is the peatland coverage and permafrost in peatland areas estimated by various methods. So this says we mapped the world's frozen peatlands, and what we found was very worrying. Why? Because obviously there is thawing and release of strong greenhouse gases like methane happening. These are the sites of methane clathrates. We talked about clathrates. They are hydrated methane locked up in high pressure in sediments and wetlands and so on. Obviously the potential for their release is very high. These are collapsing hydrates here, known and inferred hydrates over these smaller red circles, and probable hydrates estimated here based on other indirect evidences. Melting peat bogs, obviously great source of methane, and cold abyssal current and warm surface current shown for the thermohaline circulation, because if we remember our Paleocene-Eocene thermal maximum, sudden release of locked up CO2 from clathrates and peatlands can be a serious contender for abrupt climate change, and then there will be feedbacks. So we have to keep a close eye on these clathrates, but by all evidence, with works like by David Archer of University of Chicago, it doesn't seem like there is a high risk of clathrates being perturbed enough to release large amounts of methane in the coming century or two. He has made long-term projections of how it might happen if the warming continues for a long time. Okay, so methane, strong greenhouse gas, strong feedback to climate, strong impact of climate on methane, especially through wetland distribution, permafrost thawing, clathrate potential release from clathrates, and so on.